Alright, so here's a project I've been playing with. I started this over winter break. Had some time, been playing with surface mount soldering and so on. And so I decided to make a modern version of something like the old MSI 8080. So that was a system that many of us cut our teeth on as far as microprocessor design and operation, as well as assembly language programming, machine language programming, and this was where many of us learned to love front panels with blinking lights. So this is, pocket size, relatively small, 3 by 4 inches version of a complete Z80 based microprocessor. So 8080s are a little rare, but Z80s are still being made. So it's a Z80 processor, right? Good old 44 pin package, static RAM. It's hard to find 64 kilobyte static RAM, so this is actually 128. We only use half of it in here. And then just a bunch of discrete components, some logic gates, FIDI 231 serial USB converter, and some other stuff, and a good old rechargeable battery, a few rewires from errors on the boards. But this gives us a complete interface to a live Z80 based microprocessor system, and 3D printed a little case for it. So this just slides into the case, and there's a little panel that comes down over the front. So now you've got something that you can take out on the road with you if you're so inclined, and it's a nice little self-contained processor. So you can turn it on with a slide switch. And let me take out my lights. And so data bus, here's the address, here's the programmed output. This is the reset button, so you can go back to location 0 and you can examine whatever address you have specified here. So here's the contents of address 1, and examine next will take you through successive memory locations, so you can see the address bus incrementing and the data bus, the 8 bits stored in each of those locations. And if we go back to location 0, I don't know, we could deposit some arbitrary number, so I can hit deposit and put that in location 0, and then examine location 1. If we go back to location 0, there's the value that we stored. And I could store 0, and there's some deposit next button to store this 0 in successive locations. And then maybe I'll store a C3, which is a jump instruction. So I'll deposit that next, and then store a pair of zeros. And so I've just stored a jump back to location 0. So if I go back to location 0 and I hit the run button, this will just run through those first few locations. It's basically doing a few no-ops and then jumping back to 0. The address bus shows some things other than those first few memory locations, because there's a refresh cycle that goes on in the system as well. So let me stop this and let me go back to location 0 and use the step button. So here's location 0, and these lights show you the system status. So M1 read and memory request, that's an instruction fetch, that's an M1 cycle. And then we go on to the next M1 cycle is another no-op, and there's another no-op, and location 4. Location 5 is the start of the jump instruction, so that begins with a memory fetch, and then it does a memory read, but not an M1 cycle. So this is an M2 cycle. It's reading the first byte of the jump address, and then at location 7 it reads the next byte of the jump address, and then it will execute that, jump back to location 0, goes back to an M1 cycle. And you can do some things with this that you couldn't do with the old MSI. For example, by long pressing the step button, I can go from stepping one M cycle to an entire M1 cycle. So now I can go to the address, the instruction at address 2, 3, 4. There's the jump instruction. If I press this again, it will execute the entire jump instruction. So 3 M cycles, 10 clock ticks, and then go back to location 0. If I long press again, I'll get my flashing bus indication, indicating that this is now a single clock tick. So I'm about to fetch, the no-op in instruction 1. There's a memory refresh step. Here's a memory request going on, but the read access is not turned on yet. but it's preparing to do a memory request. And then there's the beginning of the M1 cycle, and then M1 memory request and read go high, and so now it's fetching instruction 2. And so that's the first clock tick, second, third, fourth. There's the next instruction at location 3. 1, 2, 3, 4 clock ticks gets the instruction at location 4. So here I can tick the clock a single clock tick at a time. And the effect is, you can press buttons and see blinking lights and so on. Or I can just go ahead and let it free run. You have front panel access to the regular interrupts, which are masked by default, but also the non-maskable interrupt. And so let me just hold that down and step the processor a few times. And after a few ticks, the system will jump to the interrupt vector, which is location 66. So let me do that again. Let's hold this down and start ticking the system, and we're going to watch the address bus down here. And there's location 66, so we've jumped to the interrupt vector. So that's the basic, most of the front panel controls that were available on the IMSI. So able to examine memory as well as examine, consecutive locations. Ability to deposit in memory, deposit consecutive locations, and then, stop, run, reset, single step, interrupts available, and so on. There's also a number of hooks in here that were not available in the IMSI. For example, there's 128 kilobytes of flash memory on the back, and you can store copies of the static RAM into files and then load them back. So for example, I can use my low address bus to pick the file number. I'm going to pick file 1, and I'm going to ask to load the first page, that's 4096 bytes, from that file into memory. And I do that by holding down stop and deposit. And when I do that, you can see my address bus is incrementing as it loads in, and then it flashes when it's finished. And what I've stored in that location is a simple counter program. So if I run this, my programmed output just counts. And I can control the speed with my programmed input, so I can make it count. Programmed input is here. So I can make it count up very slowly. Right, so that's just a good old binary counter. Or I can increase the speed by turning on different bit values. So this is the starting value that it counts down from, and I can make it go really fast like that. So you can toggle in your programs through the front panel control as usual, but you can also save these programs in flash memory and then pull them back even after power's been removed. So this system runs at around, I forget what exactly the number is, but it's around 70 milliamps, I think, and I've got a 450 milliamp rechargeable in the back. So nominally good number of hours of run off of a charge. You can charge it through the USB port. There's a reset button for the control processor inside. So there's an ATmega 328 controlling the front panel and interacting with the processor. When the Z80 is running like this, it's totally running on its own. The ATmega is out of the operation, and there's a 4 megahertz clock driving the Z80 CPU. CPU is talking directly to memory, and so on. So there's no external control involved. But when the system is stopped, this is all fly-by-wire, and the ATmega is controlling everything. So when I hit the step button, rather than directly driving the wait and bus request and so on like that, this is just an input to the ATmega, and the ATmega is controlling the clocking on the Z80 right now. When I hit the reset button, it does not directly drive the reset pin on the Z80. This is just an input to the ATmega, and the ATmega sends out a signal to cause the processor to reset, and so on. So you got a great deal of control with this hardware in a loop mode. But then if you want just the full-on Z80 experience, you can just go into run mode, and the system's off and doing its thing. So that's the basic setup. The other thing about this is if you plug in a serial port on the USB, you have a full command line interface to everything that's going on. So I'll show you that next, and that makes it a little more practical if you want to cheat and do something other than just toggle in programs through the front panel. You can do that using the serial interface.